rates of change, part 2. We're going to do a few examples. These don't take as long as the first one. I really need to introduce that particle stuff. So let's see. Let's do number 2, and it says a tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes. Then Torricelli's law gives the volume V of water remaining in the tank after T minutes as V is equal to 5,000 times 1 minus T over 40 squared. Between time is 0 and 40. So let's just write that formula down. The volume is equal to 5,000 times 1 minus T over 40 squared. And this is for values of time between 0 and 40. Let's see here, just like this. Okay, so it says find the rate at which water is draining from the tank after 5, 10, and 20 minutes. So let's hear that. The rate at which water is draining. That is the change in the amount of water. That is the change in the volume. The change in volume is dV dt or V prime of t. That's what we're trying to find. So we have to take the derivative of volume. That's what they're asking us to do. So again, this section is rates of change in sciences. So this is an application of a derivative. So it says find the rate at which the water is draining from the tank after 5, 10, and 20 minutes. So first let's find V prime of t. This is going to be 5,000 is a constant. We leave him in front. It's going to be 5,000. This is power rule. 2 comes in the front times 2 times 1 minus t over 40 times the derivative of the inside function. Derivative of 1 is 0. The derivative of negative t over 40 is just going to be negative 1 over 40. So this right here is V prime of t. We can clean it up a bit. V prime of t is 1,000, or negative 1,000 over 40 is basically what we have. This is 1,000 divided by negative 40 times 1 plus t over 40. Let's see, I could knock out a 0. 4 goes into 125, so this is negative 25 basically. That's what we have here, negative 25. Okay, so now let's see, what is V prime of 1, V prime of 2, and V prime of, wait, was it 1, 2, and 3? No, it's 5, 10, and 20. 5 after 5 minutes, after 10 minutes, and after 20 minutes. So what they're asking us to find is the rate of change of the volume at this moment in time, after 5 minutes, after 10 minutes, and after 20 minutes. So let's see what's happening. If you plug this in, if you plug in 5 for t here, what you should get is negative 218.75, and this is in gallons per minute. We're keeping with, this is the convention we're going to be using. When something's decreasing in length or amount, you get a negative. That's why we have a negative right there. So it is the volume of this is going down by 218.75 gallons per minute, 5 minutes into the drain. And then after 10 minutes, the decrease in volume, the rate of decrease is negative 187.5 gallons per minute. So what we see is, okay, a little bit later, after 10 minutes have passed, it's not draining as quickly. We see that. And then after 20 minutes, the volume is decreasing at 125 gallons per minute. So you can kind of see as time goes on, the volume, the rate of decrease of the volume it's slowing a little bit. All right, so that is the first one. Let's look at, that was number 2. Let's look at number 3. The quantity of charge, Q, in columns, C, that has passed through a surface up to time t is given by Q of t is this. So this is number 3. They give us the charge, Q, which is t cubed minus 2t squared plus 6t plus 2. So the change in the charge per time is known as current. And so dq dt is known as current, and so it is measured in coulombs per second, which is known as amps, amperes. So dq dt, what we're trying to find here, because it says find the current, which is the change in the amount of charge per time. So this is what we're after. Take this guy's derivative. This is going to be 3t squared minus 4t plus 6. Okay. And then they want us to know when time is 0.5 seconds and time is 1 second. So what is q prime? This is the same thing. Q prime of t is this. But what is it after 0.5 seconds? And what is the current flow after 1 second? All right. So if we plug this in, you're going to find that it's 4.75. And this is known as coulombs per second, but this coulombs per second is also known as amps, which is probably something you've heard of before as far as electrical current flow. After 1 second, we calculate this and we get 5 amps is what we'll get when we plug that in. So here's some applications of the derivative. Let's go on to number 4, which is finally we get to marginal cost. This is an economic application. It says C of x is the cost function for a certain commodity. Find the marginal cost, which is the derivative, C prime of x, the changing cost per amount of units being produced. Then compare the marginal cost at the production level, 100 units, with the cost of producing the 101st item. So let's have a look at this one. Number 4 goes like this. C of x is 420 plus 1.5x plus 0.002 x squared for a certain commodity. Find the marginal cost. Now the marginal cost is the derivative of the cost function, which means the change in the instantaneous change of the cost per unit of commodities produced. So it's not an average rate of change, it's how much at that moment in time when that many are being produced. So they use marginal cost to predict how much it's going to cost to produce one extra item. That's an application of this. So if we take the derivative here, it's going to be 1.5. This is 0. This is power rule. The 1 comes in front. This is just 1.5 plus 0.004x. This is the marginal cost. Okay. So what they asked us to do here was find the marginal cost and then find it at when 100 units are being produced. So let's do that. C prime of 100 is 1.5 plus 0.004 times 100. And what we get this to be is 1.9. And the units are dollars per unit. Okay? So when we're producing 100 items, okay, it is costing us $1.90. That's the rate of change of increase of the cost when we're producing that unit, the 100 unit. So it's saying, well, how much does it cost to produce the 101st unit? So you'll find that the marginal cost, C of 100, what this is telling you is the amount. This is telling you the amount it costs to produce 1 unit more. So if this was 200, then this would be how much it would cost. C prime of 200 would say how much it would cost to produce the 201st unit. If this was 250, C prime of 250 would be the amount it costs to produce the 251st unit. That's what marginal cost tells you. So in this case, it's the amount it costs to produce the 101st item. That is what marginal cost tells us, how much it's going to cost to produce the very next item. Now, let's just straight up calculate how much it costs to produce the 101st item. How you would do that, you say, well, how much does it cost to produce 101 items? and how much does it cost to produce 100 items. How we can figure that out is not put it in the derivative, but just to straight the cost function, and then we'll subtract these two. We'll say, well, what is this minus this? We'll see. Okay, so the cost of 101, we'll say 420 plus 1.5 times 101 plus 0.002 times 101 squared. And we're going to get a number there, and that number is 591.90. This is how much it costs to produce 101 items. Okay, and so this, see, 100 is 420 plus 1.5 times 100 plus 0.002 times 100 squared, and we calculate all that, and we get this is 590. And so this is the amount it costs to produce 100. So to find out how much it costs just to produce the 101st item, we would take this cost, 591.90, and we would subtract it from the cost of producing 100, 590, and we'll find that we get $1.90, which is how much it costs to produce the first item. We got that same number by simply taking the derivative and plugging in 100. What marginal cost does is it predicts the amount it will cost to produce the n plus 1 item. Okay, that's an application of the derivative. Here is the last one. It is a stone is dropped into a lake, creating a circular ripple. I imagine that you all have had this experience where you dropped a rock in some water, and you watched it, the waves from that the rock made from going in the water, kind of go out. So that's the situation. We have, we dropped something in the water, and it kind of created a little bit of a ripple that's going out, and it's sort of circular in shape. So we're modeling it off of a circle, and so this is what we have. We have dropped this little rock, and so it starts going out, and these little ripples are getting bigger and bigger and bigger. So that's what's happening there. We have this getting bigger. It says the rate that it's traveling outward is at 60 centimeters per second. Okay. The rate that it's traveling outward, how fast is this guy traveling outward? It is traveling outward at 60 centimeters per second. So that means, see this radius right here? It's changing all the time as time passes. So the radius is a function of time. The radius is equal to 60t because it's changing at 60 centimeters per second. So let's say after 1 second has passed, the radius is 60 centimeters. After 2 seconds has passed, the radius is 120 centimeters. So that's how we can think about that. It says find the rate at which the area within the circle is increasing after 1, 3, and 5 seconds. So we need to know the area formula for a circle is pi r squared. So to find the rate at which the area is increasing, we have to take the derivative. Now, they want the area with respect to time. So we need to replace r, radius, with this formula 60t. We need to talk about radius in terms of time. So let's do that. Area is equal to pi times 60t squared. Let's just replace that, and then that will be easy for us to take the derivative. This is A is equal to pi times 3600 t squared. This is the formula for area. Now let's take the derivative. The rate at which the area is changing with time is equal to, this is power rule, 2 times this big constant here. So that's going to be 7200 pi times t to the first power right there. Okay, perfect. So now this is what A of t is equal to. So if we want to know the area at these different time intervals, the area after 1 second, the area after 3 seconds, and the area of this little circular ripple after 1, 3, and 5 seconds. We just can plug this into the derivative, the rate at which it's changing. And so it's getting bigger at the rate of 7,200 pi centimeters squared per second after 1 second. And then it's getting bigger at 21,600 pi centimeters squared per second after 3 seconds. And it's changing at a rate of 36,000 times pi centimeters squared per second after 5 seconds. So, that doesn't, why are those, is this one bigger? Yes, the area is getting, the rate is increasing as time goes on of the area. Okay, so this one, what I want to do with this one is springboard into what we're going to be doing next, which is relative rates. So relative rates is where you have to write to, you take the derivative with respect to time. So I could have done the same problem right here where I made the substitution. I could have done this very differently. So what I'm going to do is the same problem in terms of related rates, which is 3.9, which is what's coming. So if they said, what rate is the area changing with respect to time, we could start right here. Let's start right here and say, well, let's figure this out. What you would do is you would take a formula that relates area and it relates radius, and what you'll do with this is you will take the derivative with respect to time of both sides of this. So this is, you'd find a formula that relates both of the things you're interested in, the rate of change of area, and we'll say, okay, take the derivative with respect to time. And what you keep in mind is that area is a function of time and radius is also a function of time. So that involves some chain rules. So what we're going to do here is say dA dt is what we get here. Here this is power rule, 2 pi r. But radius is a function of time, right? Times dr dt. So instead of substituting in this for radius, I'm just showing you how you could do this as a relative rates problem, which is what we'll have to do next. So to figure out what dA dt is, or a prime of t, which is this, dA dt, this is equal to 2 pi r times dr dt, and they told us the rate of change, dr dt is 60 centimeters, or was it centimeters per second? Yeah, centimeters per second. So what we get here is that this is 60 centimeters per second. And so a prime of t is equal to 2 times 60 times pi, which is 120 pi times r centimeters per second. And so what we would do is we would go in there and figure out what r was at the different times, and then we could plug that in at 1 second. R would be 60, and we would plug that in. So let's do a prime of 1 just to make sure we're getting everything the same. When time is 1 second, then what is the radius at 1 second? Well, at 1 second, it's 60 times 1, or 60. So it would be 120 pi times 60 centimeters squared per second. And so 60 times 120 is going to be 7,200 pi centimeters squared per second. Now, if you didn't quite get what I was doing here the second time through this problem, don't worry. But I wanted you just to have seen it one time because we're about to do related rates, and so that's this is one particular problem that you could do with related rates, and so I wanted you to introduce 3.9 with this problem. You don't have to do in 3.7. You can do it the way we just did it, but I just wanted you to see this. Okay.